Chapter 5, Force and Motion. So up to this point, we've been studying kinematics, which is the study of motion, right? How we can describe things moving, their position, displacement, velocity, acceleration, and how we can even do that in 2 and 3 dimensions. Cool, but we didn't look at what caused that motion. Why is the object accelerating? This is where we get to explore that. Forces are the things that can create changes in the motion. You know, it's not just the ball flying through the air now, but how do we get that ball to start moving? Now we can look at the before moment, before the ball is released and is launching through the air. So that's what's ahead here. First section is looking at Newton's first and second laws. So first, let's define what a force is. A force is any push or pull that's acting on an object. Another key detail is a force causes an acceleration. So those are a couple of things to keep in mind. And we're going to focus on Newton's 3 laws of motion in this chapter. This is known as Newtonian mechanics, or often just abbreviated as classical mechanics or mechanics, and it's valid for the everyday situations. It does start to break down when you start traveling at speeds that are a reasonable fraction of the speed of light. That's the field of relativity, which you'll get to take a look at in 3C for a little bit. Newtonian mechanics also breaks down on the scale of the atomic structure when things get really, really small. That's where quantum mechanics comes into play, and that's its own field and study. So Newtonian mechanics is viewed as an approximation of general relativity. And when we say approximation, it matches exactly when these conditions are met. As long as you don't have something super tiny or traveling super fast, it matches identically to it. So it's a really solid framework for viewing the world around us and most things we encounter. We don't usually encounter things traveling the speed of light or things that are at the atomic structure level, but there are things that also can be studied. So that's some of the backstory here. And it will help us to think back a little bit to before Newtonian mechanics. This gives us some context for what Isaac Newton came up with here. It was thought that some influence, what we'd now call a force, was necessary to keep a body moving, that the natural state of objects was at rest. And this seems intuitively reasonable, right? If you push something, it'll move a little bit and then it stops. So it seems like, yeah, if you really want to keep it moving, you have to keep pushing on it. So it in some ways matches our understanding. I can see why you would think that way. And a lot of times, even now, it's something we sort of think of that as the default. But this is forgetting about the fact of friction. What if we envision a frictionless surface? Sort of like an ice rink, but even more frictionless. In that case, if I gave my planner a little push, then there would be no friction to slow the object. It would just keep moving forever as long as there was no friction there at that constant speed. That's what you see in outer space, right? If once things start moving in outer space, they can keep going forever. So this tells us, hey, friction is a force that's acting on the object to cause it to come to rest. So this leads us to one framing of Newton's first law, that if no force acts on a body, the body's velocity cannot change. That is, the body cannot accelerate. So if it's at rest and there's no force acting on it, it's not going to accelerate. If we have a force acting on it, it can start to move. That's an acceleration, but it can also stop. That's a force of friction acting on it to cause it to accelerate or decelerate to slow down to a stop. So let's look a little closer at some of the characteristics of forces. So first, the unit of forces is the Newton. That breaks down to kilograms times meters per second squared. And we'll see how that breaks down when we get to Newton's second law. So that's coming. But you can note that it's abbreviated as a capital N. So that's a handy thing. That stands for Newton. Another characteristic is the acceleration of the mass is proportional to the exerted force. This is really again at Newton's second law, but we'll let it slide for now. Another detail is forces are vectors. So we're going to be back with our vector addition and dealing with those arrows on top of the things. And also often breaking our vectors down into X and Y components in order to make it easier to handle them, because vectors are kind of a pain to manipulate. The net force then is something we can define as the vector sum of all the forces on an object. It's sort of like the net profit. When you've taken into account all the different pushes and pulls, what's the net result? So the principle of superposition is one that says individual effects can be described by one single net effect. So for forces, the principle of superposition says a net force has the same impact as a single force with identical magnitude and direction. So if we've taken the net force of having a bunch of different forces on here, right? One up, one to the right, one to the left, one down a little bit. And we say, hey, the net force of this is actually just slightly up, right? Because the two left and right cancel, the down reduces the up. So that's the net force. And it turns out the sum of the forces will behave the same as if we just had a single force acting in that direction. So this gives us a restatement of Newton's first law that's a bit clearer. That says if there's no net force acting on a body, if F net is equal to 0, or that's a vector sum, then the body's velocity cannot change. That is, the body cannot accelerate. So this is a good thing to keep in mind. Whenever we notice that there's no net force, that will tell us there's no acceleration, and vice versa. So that will allow us to solve for a number of different things. Now, Newton's first law, it turns out, is not true in all frames. It's only true in inertial frames, which our book defines as an inertial reference frame is one in which Newton's laws hold. That's a little bit tautological, very roundabout, not very useful. The key is it will hold when the frame itself is not accelerating. So once the reference frame is accelerating, then Newton's laws seem a little funny. This is a little bit of an aside, but it's a useful thing for connecting to our everyday reality. So a way that we could illustrate this idea is we could consider a hypothetical situation, a thought experiment, Gedanken, a frictionless puck pushed from the North Pole, and if we view it from space, if we're viewing it from space, we'd see, okay, we push it from the North Pole, it's just traveling a straight line toward the equator, right? Imagining that this could work. Cool. But what if we view it from the ground? Well, if we're on the ground, say down here, right? Then as the puck starts traveling towards the equator, we keep rotating. So from our reference frame, it looks like the puck deflects away. It goes opposite the rotation of the Earth. This is really strange, right? What magical force is causing the puck to bend to the left? Well, it turns out there's no magical force. It's just that we are on the Earth that is rotating. Since we are traveling in a circle, we actually have an acceleration. So our reference frame, the Earth, is accelerating, and thus it's a non-inertial reference frame. So this is only true over really long distances that the ground is a non-inertial reference frame. In general, we'll treat it as inertial. So you don't really need to worry about this slide, but it's a useful addition. So like it says here, in general, we'll assume that the ground is an inertial frame. All right, so now that we've seen Newton's first law and the idea of the net force, let's take a look at a checkpoint. So which of the figures arrangements correctly show the vector addition of forces F1 and F2 to yield the third vector, which is meant to represent their net force, F net? So I'd like you to take a look at this, see what you come up with, and make sure to settle on an answer before you move on. So go ahead and pause now. Right, so as we look at these different responses, right, it mentions it's vector addition of forces. So that means we need to, if it's vector addition, we need to line them up tip to tail. And so we notice with vector A, the tip of F2 is not pointing to the tail of F1, and that actually F1, the tip of it's pointing to the tail of the net force. So this is vector addition of F1 plus F net would be equal to F2. That's not what we're looking for here. We look at case B. This is just the opposite, right? F1 and F2 are not in the right position for vector addition. This is actually vector addition for F2 plus F net would be equal to F1. Finally, let's check vector C. Notice with this one, we can go F2 is pointing to F1, follow F1. So now F2 plus F1 is equal to F net. So case C here follows the right rules for vector addition. Right, so now that we've seen those three examples, let's look at three more. Here's three different cases. I want you to look at them and consider which of the arrangements follow the proper arrangement to show the vector addition of forces F1 and F2 to represent the net force as the third vector. So go ahead and pause now. Alrighty, so here we are with three more. And one thing we can notice is that vector in case A, it looks a lot like our previous C, in that F1 points to, the tip of it points to the tail of F2, and the F net comes from the original tail and goes all the way to that final tip at the end. So this just is the commutative, right? It's F1 plus F2 as opposed to F2 plus F1, but that works just as well. So I'd say that this one checks out. Now, what about B? Notice in B, it's not lined up like vector addition. We don't have the triangles like we did before. Same with C, actually. Neither of these are triangles. So how can we tell? Well, one thing we can do is with vectors, we can move them, we can transpose them as long as we don't change their orientation or length. So we could make our own triangle. So for instance, I could shift F2 up here. As long as I keep the length the same, that's not actually changing anything. And now notice it looks identical to case A. So that's one way of looking at it. Similarly, I could shift F1 to the right. That would also work. Now what about with C? With C, if I shifted F2 up here, notice we don't now have the correct vector addition. We have F1 plus F2, that part's good, but the F net is pointing in the opposite direction. Right, where F1 is pointing up and F2 is pointing to the right, the net force should match that. It should be pointing up and to the right, and instead it's pointing down and to the left, the opposite direction. We can check that rule in general with the other arrangements here, right? F net for A is pointing up and to the right, where F1 is up, F2 is to the right. That checks out. Same thing with B. They both match on being up and to the right, whether you're looking at F1 and F2 or F net overall vector. So that's a useful frame of reference with this. So we come to the end and we see that it is C on the first round and A and B on the second round. So this is a good point to pause now that we've seen Newton's first law and how it can connect to vector sum known as the net force.